let me welcome everyone to the Oxford-Bristol Set Theory Seminar. This is the first talk of Trinity term, and we're recording the talk. We'll be posting it on YouTube later. And today's speaker is Sam Adam Day, and he's going to speak on the topic of the continuous gradability of the cut point orders of R-trees. So go ahead, Sam.
Okay, I'll just go ahead and share our screen. Let's see. Is that, can everyone see this? Okay, so yes, today I'm going to be talking about R-trees. I'm going to be talking about the underlying orders of R-trees, and I'm going to be talking about this notion of continuous gradability for these underlying orders. Of course, I'll explain all of these in due course. So just a quick summary of what I'm going to be talking about today. The talk is going to be divided into three parts. In the first part, I'm going to ask and answer a question raised by Favre and Jonsson in 2004 concerning these, what I'm going to be calling branchwise-real tree orders, which are related to the underlying orders of R-trees. And the question is, does every branchwise-real tree order admit a continuous grading? In the second part, I'll produce a characterization of when exactly a branchwise-real tree order admits a continuous grading, and this is going to relate it very strongly with set-theoretic trees. So here, because we have several different notions of tree, I'm calling these set-theoretic trees well-stratified trees. So the characterization is that a branchwise-real tree order is continuously gradable if and only if every embedded well-stratified tree is R-gradable. This means that it has a monotonic function to the reals. And then finally, in the third part, this characterization is put to work, answering various refinements of the main question raised in the first part. So this is where we look for branchwise-real tree orders with additional properties and ask whether or not they can be continuously graded. And some of these questions will lead to some independence results. But throughout, please do interrupt if something is not clear, if you have any questions.
Sam, might you post your slides in the chat so that people can look at them and look back?
Yeah, sure, I can do that. Let's see.
Thank you very much.
Okay. So, what is an R-tree? Well, the way to think of an R-tree is that it's a metric space tree in which every point can be branching. Alternatively, you can think of it as an R-tree is to the real line what a normal kind of graph-theoretic tree is to the integers. Now, R-trees play an important role in geometric group theory, where we consider infinite groups acting on these objects. And they're also interesting objects in their own right. Okay, so how do we define them? Well, first of all, if we have a metric space, then a geodesic segment in a metric space is the isometric image of a real interval. An R-tree is then a metric space such that between any 2 points, x and y, there is a unique geodesic segment of length at the distance between those 2 points. And I'm going to be using interval notation for these geodesic segments. So the geodesic segment between x and y is going to be notated using this interval bracket notation. Okay, so let's have some examples of some real trees, some R-trees. Well, first of all, if we have any tree in the graph-theoretic sense, by which I mean a collection of vertices and a collection of edges, which is connected and without cycles, then this can be turned into an R-tree by simply laying a copy of the unit interval norm 1 along each edge. This is what's sometimes known as the geometric realization of this graph-theoretic tree. And it produces what's known as a simplicial tree. Okay, but the class of R-trees is a lot more general than this, because we can allow every point to be branching, or we can allow any point to be branching, I should say. So this means that we can have branching points with arbitrary distance between them, arbitrarily small distance between them. So here's an example of an R tree which cannot be viewed as the realization of a graph-theoretic tree. So what we do is we take the real plane and we designate each point along the x-axis as a train station. And then every vertical line, as well as the x-axis, as a train track. And then we can use this to define a new metric where if you want to travel between any 2 points, you have to travel along the train tracks, potentially passing through the stations. So the distance between any 2 points is the distance traveled when restricted to these train tracks. And then once we give it this metric, the real plane does indeed become an R tree. And the way to think about it is that it's one long line, i.e. the x-axis, and every point along the x-axis is a branching of degree 4. Okay, so in this talk, what I'm going to be mostly interested in is the underlying order of these R trees. So given any R tree and any point in there, we can take what's known as its cut point order, which is the result of defining an order in this way. So if we take P in X, then the cut point order on X with root P is defined by X is less than or equal to Y, if and only if the geodesic segment going from P to X is contained in the geodesic segment going from P to Y.
Excuse me.
So this is, sorry.
Could I interrupt for a moment just to make sure I understand definitions correctly?
Sure.
If I take the plane with the usual metric,
Yeah.
that seems to be an R tree also, is that correct? Between any two points?
No. Because you can have all sorts of geodesic segments going between any 2 points.
But in the usual metric, that wouldn't be geodesic, only the straight line would be
Oh,
geodesic.
that's true, actually, yes, of course, because they have to be of the length. So maybe the definition is a little ambiguous. What I should say is there is a unique geodesic between any 2 points, and that unique geodesic has length, the distance between those. Does that clarify?
Let's see. Say that again. I
Okay.
missed something there.
Okay, so this definition, maybe I should make it a little clearer. I should say instead of there is a unique geodesic between any 2 points of length dx, I should say instead there is a unique geodesic between any 2 points, and this unique geodesic segment has length, the distance between these 2 points.
Yeah, good. That seems, at least it solves my current problem.
Right.
I'll try not to come up with any new ones.
Okay. All right, so we have this cut point order here. And well, in 2004, Favre and Jonsson, they published a monograph called The Valuative Tree, which investigates lots of different things. But in particular, they're looking at this order structure which arises from R trees. And one of their aims is to find an order-theoretic characterization of the types of orders that can rise as cut point orders of R trees. So in order to follow their discussion and lead to the main question, I'm going to replicate their definitions here with a few changes of terminology. So the main object of study, which we're going to be looking at throughout the presentation, is the notion of a branchwise-real tree order. So a branchwise-real tree order is a partial order subject to the following 4 conditions. The first one says that for any x, the set of predecessors, which I'm going to call the down set, this thing is linearly ordered by the partial order relation. The second condition is that x has a minimal element, a root, which lies below everything. Okay, so these 2 conditions correspond to our intuition that a tree should be something that is connected and without cycles. The third condition is that x should be what's known as a meet semilattice. So this is that If you take any 2 points, then they have what's known as a meet, which is a maximum element in the set of elements that lie below both of them. And then finally, the fourth condition is where the branchwise-real part comes in. This says that a branch, by which I mean a maximal chain, every branch is order-isomorphic to some real interval. So in their monograph, Favre and Jonsson call such objects non-metric trees. Okay. Now we have our branchwise-real tree orders, so I need to define continuous gradings. So first of all, what is a grading? Well, let's let P and Q just be arbitrary partial orders. Then we say that a P grading Q is just a strictly monotonic map going from Q to P. And then a continuous grading of a branchwise-real tree order is an R grading subject to the following continuity condition. The condition is that whenever we have x less than y in the branchwise-real tree order, if we restrict the grading to the set of elements between x and y, and I'm using interval notation again for this, the set of elements between x and y, then this restriction is an order isomorphism onto the real interval, which lies between the image of x and the image of y. So Favre and Jonsson call such functions parameterizations. Okay, so let me now state the characterization which Favre and Jonsson obtained. The characterization is that the class of R-tree cut point orders is exactly the same as the class of continuously gradable branchwise-real tree orders. Okay, so I'm not going to prove this, but I'm going to use this as a starting point to ask the question, because one might wonder, is this adjective continuously gradable necessary in this characterization? One might imagine that because every branchwise-real tree order has every branch order isomorphic to a real interval, that somehow these order isomorphisms can be glued together in a continuous way, in a consistent way to produce a global continuous grading. But in their monograph, Favre and Jonsson state that they do not know whether there is a non-continuously gradable branchwise-real tree order, or in their terminology, a non-parameterizable non-metric tree. So inspired by this, our main question is every branchwise-real tree order continuously gradable? And spoiler alert, the answer is actually no. This is what I'm going to answer now. So this is a section where I answer the main question. The theorem is that there is a branchwise-real tree order which is not continuously gradable. So I'm going to produce a counterexample to the previous question. And the way we're going to do this is we're going to take what's known as the road space of a well-stratified tree. So let me just first define well-stratified tree formally, so the definition is here. A well-stratified tree is just a rooted partial order in which every down set is well ordered. So this is just what the set theorists mean when they talk about trees. And then if we have any arbitrary well-stratified tree, we can take what's known as road space. Its road space is the partial order obtained by replacing every node with a copy of the half open interval 0, 1. So the way to think about this is that we're going to be drawing roads through all of the branches of the well-stratified tree. Actually have a picture in the next slide. So let's just take some random well-stratified tree. The well-stratified tree is going to be the collection of these nodes here, and then we have a light gray line between nodes indicating that one is above the other. And I've indicated the levels of this tree, and it goes up to omega plus 2. And then the road space of this tree is going to look like this. So we just draw roads going throughout the whole tree. And as you might imagine, this is usually a branchwise-real tree order. Indeed, when T is a Hausdorff well-stratified tree with no uncountable branches, its road space is a branchwise-real tree order. So when I say Hausdorff, what I mean is that limits in the well-stratified tree are unique, or alternatively that the tree is Hausdorff in the tree topology, or equivalently that the tree is a meet semi-lattice. So now, to prove the theorem, it suffices to take the road space of a Hausdorff R-gradable well-stratified tree with no uncountable branches. Why is this the case? Well, if we have such a tree, a well-stratified tree, then we can take its road space, and we know that that's going to be a branchwise-real tree order. Furthermore, it can't possibly be continuously gradable, because if it's continuously gradable, then in particular, it has an R grading, and this R grading is going to restrict to an R grading of the original well-stratified tree, which always sits inside its road space. So we've now effectively transformed the question coming from R trees and their orders to one which is purely set theoretic. Can we find such a tree? Well, yes, we can. In 1970, Baumgartner proved that such a tree exists using results from Gavin and Labour. So the theorem is there is a Hausdorff R-gradable well-stratified tree with no uncountable branches. I'm not going to prove it completely. I'm just going to give you an outline of how it works. So let's take the tree of all injective functions going from some ordinal into omega. So we take the tree of all functions where the image is some countable, where the domain is some countable ordinal, and the image is omega, or a subset of omega, let's say. And we order this set by function extension. Then it's not hard to see that the result is a well-stratified tree. It's Hausdorff and it has no uncountable branches. Moreover, we can see that the tree cannot have any Q gradings. And the way we do this is by a forcing style argument due to Labour, where we show that the tree cannot be special, i.e. cannot be the union of countably many antichains. Okay. So we have this non-Q gradable tree, but what we want is a non-R gradable tree. So in order to get this, we need to exploit a trick due to Gavin, which is that we shift all of the nodes of the tree up a little bit, up by 1. So let shift of this tree be the result of replacing every node on a limit level with 2 nodes, one above the other. So effectively what we've done is we've shifted all of the nodes up by 1 and added new nodes along the now empty limit levels. And then by a result of Gavin, in fact this holds true for trees, well-stratified trees in general, any R grading of the shifted tree corresponds to a Q grading of the original tree. And thus the shifted tree has no R grading. And thus, putting this all together, we have a proof of this result. So what we do is we take this tree, we take this tree, sorry, this is the thing I want. We take this tree from constructed by Baumgartner, and we take its road space, and this gives us a branchwise-real tree order which is not continuously gradable. Okay, but there's more to be said. So in the second part, I'm going to look at characterizations of what does it mean for a branchwise-real tree order to be continuously gradable. And so this is the characterization which I'm going to prove. A branchwise-real tree order is continuously gradable if and only if every well-stratified subtree is R-gradable. So this means that the use in the previous section of this R-gradable well-stratified tree with no uncountable branches is in some sense essential, because whenever we have a branchwise-real tree order, which is not continuously gradable, then it has to contain within it an R-gradable well-stratified tree with no uncountable branches. So the way that the proof works is we're going to take an arbitrary branchwise-real tree order and construct an increasing omega sequence of well-stratified trees, which somehow approximate this the original branchwise-real tree order. And this is going to be such that the union of these trees will be dense, in the sense that whenever we have x less than y in the branchwise-real tree order, there's going to be some z in the union which lies between x and y. Okay, so here's how we do it. This is how we construct our increasing sequence of well-stratified trees. So let's let x be our branchwise-real tree order. What we're going to do is we're first going to fix an enumeration of the rationals between 0 and 1. And we're going to fix a well-ordering of the branches of x into b alpha for alpha less than some kappa. And for each b alpha, since x is a branchwise-real tree order, we can fix some isomorphism onto a unit interval. So we have some isomorphism onto a real interval, but we can always stretch it to make sure it's a unit interval. And then what do we do? Well, to define our Tn, at Tn, we're going to walk through all of the branches in their order. And on the final segment of the branch, which hasn't been considered in the previous branches, we're going to add the pre-image according to the fixed isomorphism of the branch onto the unit interval of this set of n plus 1 rationals through 0 to the qn. Okay, so I have a picture on the next slide, but formally this is how we define our Tn. So we take the union of all the branches, and we take the pre-image with respect to the fixed isomorphism of q0 up to qn, but then we throw away the bit of that pre-image that lies inside any of the previous branches in the iteration. Okay, so here's the picture. So let's say we're at stage b alpha, stage alpha, and we have a branch b alpha. So the branch is this blue thing here. And then in gray, I've represented all the previous branches of stages below alpha. Okay, now b alpha has our fixed isomorphism onto unit interval. And inside our unit interval, we have our n plus 1 rational numbers. And then we can take the final segment of b alpha, which it results from throwing away all the stuff from the previous b alphas, b betas, sorry. And then finally, what we do is the nodes added at stage alpha will be the pre-image according to R alpha restricted to this final part here. So these black dots on the left are the elements that we add at stage alpha. Okay, so first of all, we need two basic properties of this iteration, of this sequence. The first is that every Tn is indeed a well-stratified tree, and it has no uncountable branches. Well, this follows from the fact that we take a well-ordering of the branches, and the fact that at each stage we only take the pre-image of a finite set, so we just add finitely many new things at each stage of the iteration. And the second fact is this density result, which is that for any x less than y in the original branchwise-real tree order, there is some z in some Tn which lies between x and y. And the reason for this is because eventually on every one of these final segments, we're going to be adding the pre-image of every rational number. So eventually we're going to be getting dense inside the union. Is there a question? I can't see the questions. If there's a question, please tell me. Okay. Now, another result which I'm going to need to prove the main theorem in this section is about continuifying R-gradings. So when we find a continuous grading, continuous grading is going to be an R-grading subject to this continuity condition. But what I'm going to need is that actually this continuity condition can be eliminated in the sense that a branchwise-real tree order is continuously gradable if and only if it's just plain R-gradable. In other words, whenever we have an R-grading, we can transform it into a continuous grading. This is what I mean by continuifying. So the lemma is as follows. If a branchwise-real tree order has an R-grading, then it has a continuous grading. So when we have this R-grading, we essentially have so this is a monotonic map, but it might have a bunch of jumps in there. And the idea is that we want to go through and eliminate all those jumps. So I'm going to do it with a Zorn's lemma style argument. In fact, I strongly suspect that we need some kind of choice in order to make this work. So here's how it works. By Zorn's lemma, there is a maximal partial continuous grading whose domain is downwards closed, which is always gets less than our R-grading f. So what does this mean? This means that we're taking an R-grading L, whose domain is downwards closed, such that restricted to its domain, it's a continuous grading. And we also require that L is less than or equal to F. And so by Zorn's lemma, there is a maximal such one. So of course, what we're going to show is that its domain must be the whole of X. So let's assume for a contradiction that its domain is not the whole of X. Then this means that there's some element not in the domain, and in fact we can pick some maximal chain not in the domain. Now, because X is a branchwise-real tree order, and because the domain of this L is downwards closed, C has got to look like an interval, and F on C has got to look like a monotonic function. So what we're going to do is we're going to import a result from analysis. We just have this function, which is monotonic on an interval, and we can always find a continuous monotonic function on this interval, which lies below that function. So indeed, we can do that, and then we can use this to extend f on C below on C, such that it still lies below. Sorry, we can use this to extend L on C so that it still lies below F. And this then contradicts the fact that L was maximal. On the next slide, I have another picture for this. Okay. So here's the picture. We have our tree, and at the bottom we have the root node, and then we have this L, and it's not defined on the whole of the tree. It's just defined on this shaded in section here. And then we find some maximal chain C, which is outside of the domain. And then if we look at what F does on this chain, it's going to look maybe like this when we have a bunch of jumps. And then what we do is we just find something which lies below all these jumps and extend L like this. Of course, in general, there could be, the jumps could be dense, so this picture is not representative of the general case. But we can always find this continuous monotonic function, even when we have dense jumping. Okay, and then the final result, in order to establish the characterization in this section, is relating R-gradability of the original branchwise-real tree X with the R-gradability of each of the approximating well-stratified trees. So the result is that X is R-gradable if and only if each Tn is R-gradable. And here's how we do it. Well, let's assume that each Tn is R-gradable. So we have a function Fn going from Tn, and we can assume that the image is a subset of the open interval 0, 1. And each Fn is an R-grading. So what we're going to do is we're going to combine all of these R-gradings together into one R-grading of the whole branchwise-real tree order. So the first thing we do is we extend each Fn to Fn hat on the whole of X, weakly monotonic. So there are many ways of thinking about this, but the simplest way to explain is that if we take any point of X, we can look at the supremum of the values that Fn takes below X, and we let Fn hat of X be the supremum. Then this then defines a weakly monotonic function, and it also extends Fn. Okay, and then to define our F, what we do is we take a little bit of each of these Fn hats. So in particular, F of X is going to be the sum of Fn hat of X divided by 2 to the n for each F. So of course, Fn hat is bounded above by 1, so the sum always converges. And it's straightforward to see that this thing defines a definitely weakly monotonic function going from X into 0, 1. So all we need to do is to show that it's actually strictly monotonic. So here's how we do it. We're going to use the density result. So let's take X strictly less than Y in X. We want to show that F of X is strictly less than F of Y. Then, by using the density result, there is some Tn and X0 and Y0 in Tn, such that X is strictly less than X0, which is strictly less than Y0, which is strictly less than Y. And then, because X0 and Y0 lie in Tn, then Fn hat of X0 is strictly less than Fn hat of Y0. And then, so this means that F of X0 is strictly less than F of Y0. And then finally, F of X is less than or equal to F of X0, and F of Y0 is less than or equal to F of Y. So this gives us the result. Okay, so let's prove the theorem of this section. I'm just going to state it again. The theorem is that a branchwise-real tree order is continuously gradable if and only if every well-stratified subtree is R-gradable. That's how we do it. The left to right is straightforward. So if we have a branchwise-real tree order X, which is continuously gradable, then in particular it has an R-grading. And then this R-grading is going to restrict to an R-grading of any well-stratified subtree. Conversely, let's assume that X is not continuously gradable. Then by this continuifying result, a couple of slides ago, this means that X can't be R-gradable either. If it were R-gradable, then we could continuify this R-grading into a continuous grading. And now let's take Tn, the sequence Tn, to be this approximating sequence of well-founded subtrees. Then because X is not R-gradable, by the previous lemma, at least one of the Tn must not be R-gradable. If they were all R-gradable, then X would be R-gradable. And so thus we have found our Tn, which is going to be a well-stratified subtree of X, which is not R-gradable. Okay. Actually, I'm just going to get some more water and give a little break of 1 minute. Maybe it might be useful. I'll be back in 1 minute. Okay, that was a short 1 minute. Are there any questions at this point? Okay, so we're now going to move on to the third part of the talk, where we consider various refinements of the main question. So what we're interested in is which properties of branchwise-real tree orders imply continuous gradability? Or conversely, can we find examples of branchwise-real tree orders which are not continuously gradable but also satisfy additional properties? And the first such type of property that we're going to be looking at is inspired by the real-world applications of R-trees. So R-trees which are used in applications are often separable. Now, separability, of course, is a topological property which applies to R-trees, but it has a correspondent on the order-theoretic side, which is a notion which I call countable wispiness. I'm going to define this on the next slide, but for now, what this third bullet point means is that an R-tree is separable if and only if each of its cut point orders is countably wispy. So this means that separability for R-trees corresponds to countable wispiness for the partial orders. Okay, and then motivated by this, we can ask the question: is every countably wispy branchwise-real tree order continuously gradable? So this is a refinement of the main question where we've just added this adjective countably wispy. Okay, and what I'm going to show is, in contrast with the main question, the answer to this question is actually yes. Countable wispiness implies continuous gradability for branchwise-real tree orders. Okay, first, let's define what countable wispiness means. So before I do that, I need to define what it means for a point of a branchwise-real tree order to be branching. Because these branchwise-real tree orders can be branching in all sorts of places and you can have quite intricate structures, the notion of branching needs to be defined quite carefully. So here's how we do it. Let's take some x, an element of our branchwise-real tree order. Then we say that an x-connected component is an equivalence class in the subset of the branchwise-real tree order of elements lying strictly above x under the following relation. Y is related to z if and only if there is some w which lies below y and z, which is also lying strictly above x. Now, any partial order, and in particular branchwise-real tree orders, can be given a natural topology called the Alexandrov topology, in which the open sets are exactly the upwards closed sets. And then under this topology, the x-connected components are exactly the connected components in this, this subset, the set of elements lying strictly above x. And then we can say that the degree of a point x is the number of x connected components. We then say that a point x is branching if it has degree strictly greater than 1. And then the other auxiliary definition which I need is the notion of a twig. So a twig is just some kind of stub in a branchwise-real tree order. So it's a maximal upwards closed subset, which is isomorphic to a real interval, non-trivial real interval. So it's something which just looks like a little line, has no branching points along it, and it's terminal. Okay, now with these two definitions in place, we can define countable wispiness. So we say that X is countably wispy if it contains at most countably many branching points, and at most countably many twigs. So it's not very, it doesn't branch very often, and it doesn't have too many stubs hanging off the end. Okay, so here's the answer to the question raised at the start of the section. The theorem is that every countably wispy branchwise-real tree order is continuously gradable. Okay, how do we do this? Well, we're going to use the characterization of the previous section. Let's let X be any countably wispy branchwise-real tree order. And to show that it's continuously gradable, it suffices to show that every well-stratified subtree is R-gradable. So let's take such a well-stratified subtree T. Now, because T is a subtree of X, it has at most countably many branching nodes. And this means that we can find a Q grading of these branching nodes of T. And then because in T all branches are countable, this means that we can extend this Q grading of the branching nodes to an R grading of the whole of T. And then once we have that, because T was arbitrary, by the characterization in the previous section, X must be continuously gradable. Okay, let's ask some more questions. Let's generalize to kappa separability. So separability can generalize to kappa separability, by which I mean there is a dense set of size strictly less than kappa. We can easily generalize countable wispiness to kappa wispiness, which means that there are fewer than kappa many branching nodes and fewer than kappa many twigs. And this correspondence, which I mentioned in the first part of the section, still holds. So an R tree is kappa separable if and only if all of its cut point orders are kappa wispy. And then we can ask the following generalized refinement of the main question. Is every kappa wispy branchwise-real tree order continuously gradable? And it turns out that in general, the answer to this question is independent from ZSC. For certain kappas, we have some independence results. Specifically, if we look at the tree constructed in the second section, this is actually going to be continuum plus wispy. It's not hard to see that it has continuum many branching nodes and continuum many twigs. Thus, under the continuum hypothesis in particular, there is a branchwise-real tree order which is kappa wispy for every kappa of size at least LF2, and which has no continuous grading. Because if we take this tree, then under the continuum hypothesis, it's LF2 wispy, and so it's also kappa wispy for every kappa bigger than equals LF2. Conversely, if we look at cardinals below the continuum, then we can use MA. So under MA kappa, Martin's axiom at kappa, every kappa plus wispy branchwise-real tree order is continuously gradable. How do we do this? Well, we use the characterization again. We take some branchwise-real tree order X, which is kappa plus wispy, and we assume MA at kappa. And we take some well-founded subtree T of X. So as in the previous proof, this must have at most kappa many branching nodes. And so what we can do is we can use the specializing forcing and MA kappa to produce a Q grading of the branching points. And then, as before, this Q grading of the branching points extends to an R grading of the whole tree T. And so we have the result. Okay, in this last section, I'm going to be looking at a refinement of the main question motivated from a different question, from a different direction. Now, when we were constructing our branchwise-real tree or branchwise-real tree order with no continuous grading, what we needed was this R-gradable well-stratified tree with no uncountable branches. Perhaps some of you might have noticed that, in fact, a Suslin tree is such a well-stratified tree. So it's natural to ask, what happens if we take this road space of a Suslin tree? What's it look like? Well, of course, it's going to be a branchwise-real tree order, and it's also going to be CCC. So we can ask this question: is every CCC branchwise-real tree order continuously gradable? And as you might have guessed, the answer to this depends on the Suslin hypothesis. Okay, so before I present that, I just want to relate this notion of CCC for the orders with some topological notion on the R trees. So let's say that topological space is boundary countable if the boundary of every open connected subset is countable. Then this result is that an R tree is boundary countable if and only if each cut point order is CCC. So this means that CCC-ness for the cut point orders corresponds to boundary countability for the R trees. Okay, so here's the result. The statement that every CCC branchwise-real tree order is continuously gradable is equivalent to the Suslin hypothesis. So we have this nice independence result. Does CCC-ness imply continuous gradability? Well, that depends on the Suslin hypothesis. And here's how we do it. For the left to right, note that if we have, let's assume that we have a Suslin tree, then we can take its road space, and its road space is going to be a branchwise-real tree order. It's not going to be continuously gradable because Suslin trees never have R gradings, but it is going to be CCC. Conversely, let's let X be a CCC branchwise-real tree order with no continuous grading. By the characterization in the second part, there must exist a subtree, well-satisfied subtree, which has no R grading. This subtree is well-stratified and is CCC. Moreover, it has to have height omega 1 because it doesn't have an R grading. Any tree which has height a countable ordinal has to have an R grading. And thus, this subtree is a Suslin tree as required. Okay, before I wrap up, I just want to mention a new direction in this project, which is looking at these branchwise-real trees directly without looking at their relationship with R trees. And we can ask some questions about the structure of these trees and whether we can produce examples that look interesting and exotic. So in particular, we can talk about rigidity analysis. So we say that the partial order is rigid if it has no non-trivial automorphisms. And then we can ask, can we find a rigid branchwise-real tree order? Well, in fact, we can, and we can find one satisfying various additional properties. So for kappa less than or equal to the continuum, there is a rigid branchwise real tree order, which is also continuously gradable, and moreover is such that every branching node has degree kappa. So somehow the rigidity of this tree is not resulting from the fact that we have lots of different degrees going on, because all of the branching nodes have degree kappa. So there's some other structural property of the tree which is making it rigid. I'm not going to prove any of these results, I just want to give an indication. And then the final thing I'm trying to mention is that we might think about making this stronger. What if we ask, in addition, that not only that every branching node has degree kappa, but that every node is branching and has degree kappa? So somehow we have this tree which is just branching everywhere all the time. Can we find a rigid one of those? Well, we can certainly force one. So there is a forcing extension containing a rigid, continuously gradable, branchwise-real tree order in which every node has degree kappa. This is, I found this a bit surprising. I think it's quite cool. I'm not sure yet whether we can force or whether it's consistent that these don't exist, but certainly we can force them. Anyway, for now, I want to finish up. Maybe just mention the main takeaways from this talk. So we have this question of Favre and Jonsson. In the first part, I answered this and I showed that there is a branchwise-real tree order without a continuous grading. In the second part, I produced a characterization of when a branchwise-real tree order has a continuous grading, which is more set-theoretic in nature. And then in the third part, we were looking at refinements in the main question. We see that countable wispiness implies continuous gradability. However, kappa wispiness implies continuous gradability only in certain situations and certain additional assumptions. And finally, CCC-ness implies continuous gradability precisely under the Suslin hypothesis. But for now, that's all I wanted to say. So thanks everyone for listening.
Well, thank you very much, Sam. So we can all thank the speaker, and we could go to, should we take a few minute break, Sam, or do you want to go right into questions?
I'm happy to go straight away, or however you like.
Okay, so are there any questions? Go ahead, Philip.
So thanks, Sam. That was very nice. Of course, it's sort of talking about Suslin trees begs the question about Arengine trees, since you're talking about uncountable branches. Do Arengine trees play a role in here?
Not so much. The reason is because when we take the road space of an Arengine tree or of any tree, we often lose this notion of levels. So for example, if we just have a look at this picture here, where I take the road space, yeah, a lot of these levels get lost. And so this somehow means that the notion of level doesn't have such a natural correspondent on the R tree side. So this is why I haven't been looking at it so much. Haven't been looking so much at these refinements of the questions that might produce different kinds of Arengine tree.
But can't you cover the levels, Sam? Because the levels will be, I mean, if in the Arengine tree every node is branching,
yeah,
the levels will just be the branching nodes, right? And every node in the road space will have a well-ordered sequence of branching nodes below it, right?
This is true.
And you'll get the levels that way, won't you?
Yes, but also, well, that's only when you have your root point fixed, because of course you could always take some other root point somewhere else, and then it messes around with the levels a bit.
How badly does it mess things up? Might it, for instance, be messed up in general, but still okay on a club of quasi levels or something like that?
Possibly. This is something I haven't thought about. But yeah, it seems like you might be able to. So if you want to get from one root to the other, I guess you're only really going to be passing through so many levels. And if you're only going to be passing through counting many levels.
That should be a bounded change. And the erasure of all the dots in your picture, of course, also messes up levels. But again, it seems to me that that should catch its tail occasionally, and there might be a club of things that you could reasonably call levels. Or there might be a set of levels defined not as an actual set, but as a set modulo the club filter or something. There might be something reasonable hiding behind all this messed up level structure.
That sounds very interesting. Thank you very much. I'll think about that.
Are there other questions? So I have a question. Can you draw us a picture possibly of this tree at the end where, I mean, the branchwise-real tree where every node has, say, degree 2. Because it's sort of hard to imagine. I mean, it's a branchwise-real tree, so there's this continuum between any 2 points, but all those points have degree 2, and so how should I think about it?
Yeah, it's difficult to draw it. I don't think I could draw it. I don't have anything to draw anyway. But maybe one way of thinking about it is you kind of have this iterative construction where you just start with a line, and then at each point you send off new branches at each point, so to make it so that it has every point is degree 2. And then on each of the new branches you do that again. And then you do that again and again, omega many times. It might happen, what you produce in the end is actually a very simple tree, which is not going to satisfy this rigidity. So somehow you need to keep going, because you might have a sequence. You might go up one branch a little bit and then go up another branch a little bit less and a little bit less, etc. And you have this kind of spiraling sequence. And you might want to add a new point at the end. And you can certainly do that and still produce a branchwise-real tree order. So in that sense, we can kind of keep going on beyond the omega step and add a new point and then a new line and then keep branching those ones, etc. And so you can kind of keep doing this omega 1 many steps. So this is the way that I've been thinking about these kind of trees. It's very bushy in a sense. And you have this, you can kind of stratify them in this sense into performing this iteration after some number of steps.
So can you maybe describe the forcing conditions that you use to force this tree, the rigid one?
Yes.
2 or whatever, kappa.
So let's see, what's the simplest way of doing this? Well, what we can do is we can take trees that look like branchwise-real tree orders, but are only countable. So we can assume that so for any branchwise-real tree order, we can take an intersection with, we can take kind of like what the rationals look like. And if you don't have too many branching points, then the resulting tree is going to be a countable tree. And so what we're going to do is we're going to force with those kind of trees. But moreover, we're going to force with promises as well. So we're going to take the forcing notion, which is these trees under subset extension, under subset. So we can always take a bigger tree, which, for example, if we take any point, we can add a new branch going off there and just add the rationals. So we force under that. And then the promises are going to be that once we have some branch, we can say, I'm going to promise never to extend above this branch. So I'm going to say that we kind of seal off a branch. So then the forcing conditions are going to be pairs of these kind of sub-branchwise-real tree orders, together with promises never to extend above certain branches. And then once you have this, you can do a kind of countable closure argument and show that if you have any candidate automorphism in the generic extension, then you can always seal off one branch and not another one to kill off that automorphism.
Okay, very good. Are there any other questions? So I was thinking about Andreas's question, and I think he's right, actually, because in the real plane, there is a unique geodesic between any 2 points, the line that connects them. So I think the definition should be slightly different, namely that for any 2 points, what you want is a unique embedding of the interval that goes from this point to that.
I think the difficulty here, at least where I got into trouble, was that the definition of geodesic talks about isometric embedding.
Yeah.
And I'm taking that to mean that the distance along the curve should be the same as the distance in the space itself, which would force the geodesic.
A straight line.
But if you say isometric embedding to be distance measured along the curve is the same as on that real interval, then what Sam was saying about curvy things counting as geodesics becomes correct. So I think the difficulty is an ambiguity in this notion of isometric image of a real interval. Does it have to be, does the metric on the real interval have to correspond to the metric measured along the curve in your space, or does it have to correspond to the actual distance, the metric in the space?
But doesn't geodesic always mean the latter? I mean, that in a metric space.
Oh, that's what I was assuming. But,
that's a good point. I hadn't thought about that. Yeah, I guess I got a bit confused with that notion. I was thinking, of course, as distance along the curve, but I think that is the wrong way of thinking about it.
Yeah. In any case, just if you say exactly which one you mean, then I think there will be no problem.
Yeah, yeah.
All right, any other questions? So if not, then why don't we thank Sam again for a great talk. And next week, I guess it's next week, we have Sandra Muller, who's going to be speaking on the strength of determinacy when all sets are universally bare. So please come back next Wednesday at 4:30, and we'll be posting this video on the YouTube channel for the set theory seminar. So thanks very much, and hope to see everybody back next week.